Oh man, 9:45. All right, give me one sec. We're getting started on YouTube. I think we got everything else ready to go. Just want to make sure this is up and running. And we're good. All right. It's man, it's pretty light Tuesday. Pretty light Tuesday. Let's get rolling. Lord, thank you for bringing us together this morning. Thank you for everything that you do for us. Pray that you would continue to bless us, help us to finish out this semester strongly, to get through the next 2 weeks, keep our focus and our composure. In your name we pray. Amen. All right. So, all right, let me see. Hopefully I have my clicker with me today. No, that's broken bar. Definitely not a clicker. All right. Here we go. I've got it. So, hope everybody is doing well, having a fantastic Tuesday, right? Before we launch into everything, I didn't prepare a slide for it, but you guys all know that the grades were posted for the exams, right? Let's talk exam stats, and then I will finish up the story at the beginning of the next exam, right? And then I'll post a video on YouTube telling you how it ended after the final exam. That's how it's going to work. So the 9:45 in-person section had a class average of a 59.56% with a standard deviation of 16.83%. You guys did best on the op-amp problem, and you did worst on the Laplace transform method problem. So the one where you're given the differential equation, and you had to use the Laplace transform method to find the response. Okay. The TOS section, and let me make sure that there's nobody sitting in the waiting room right now. Of course there are. Here we go. Trying to get better, guys. I'm trying. The TOS section, you guys had an average of 49.1% with a standard deviation of 14.79%. You guys did best on the op-amp impedance problem, and you also did worst on the same problem, the Laplace transform method problem. That's what you guys fell short. Okay. All right. So now that that's out of the way, right? You guys, I still haven't posted feedback yet. That's because over the weekend I don't have a great scanner. And as much fun as it would be for me to take pictures of all of your tests one page at a time and then load them up into LabCloud, I'm just going to do it today and use the scanner in the office. So I will post feedback so you guys can look at that. The other option that we have is I might be able to do it through test mods, where you just access your exam through test mods and you'll be able to look at the comments that are left there. So I'll send an announcement out later detailing how you can get feedback, okay? All right. So today, right, what are we doing? Well, we're going to recap. We're talking about Bode diagrams for second order systems, and then we're going to launch into vibration and vibration isolation. Okay. Pretty much right where we want to be for the end of the semester. We've got, including today, 3 actual lectures and then the exam day, right? So not that much more time left here. Bode diagram seems to be the big issue. Yeah, Sean. The lab was due yesterday or last Sunday. The benchmark is due on the 20th. I've got a list of due dates coming up in a second. Don't worry about it. Okay, so Bode diagram. What is a Bode diagram? Right? It's confusing. It's new, right? We're going to spend some more time going through them here and how to use them, right? But what do we need to know specifically, right? Well, Bode diagram itself is telling us how the magnitude and phase of our system changes as a function of frequency. They are only good for frequency response, right? So if you're given a sine or cosine input, right, where you're asked to find the steady state response to a sine or cosine input, right, then we need to be using that equation we set up in class a couple of days ago or a couple of sessions ago, right, where we have YSS is equal to the magnitude of the sinusoidal transfer function times the original amplitude of my sine wave times sine omega t plus phi, right? And we find that magnitude by finding the sinusoidal transfer function. We'll go through this all again. And the process doesn't change for doing that, whether you have a first, second, 10th order system, right? It's the same thing. As long as you have the transfer function, you find the sinusoidal transfer function, and then you just do the magnitude, right? So you do Pythagorean theorem of the real and imaginary on the numerator and the denominator, find that scaling factor, and then you take the tan inverse of the numerator minus the tan inverse of the denominator, right? Where you have imaginary divided by real inside your tan inverse. Okay. The Bode diagram itself is very useful, and we'll see a couple more applications of it in a few minutes when we go through another example, right? But the idea here is that because we can characterize the steady state response of a system to a sine wave using this equation, right? And this is a function of the magnitude and the phase of the system. If we can calculate magnitude and phase, right, or if we're given a Bode diagram where we can read magnitude and phase off of the Bode diagram, we should be able to reverse engineer our steady state input from that, as long as we know what the input frequency is and the amplitude of our input function, right? So that's one way that we can use Bode diagrams. We're gonna watch a video towards the end of class, or middle of class, regarding Bode diagrams as well, that I think might help a little bit of it. Higher order Bode diagrams, we'll get there. We're gonna get there today. That's the whole thrust of the first part of class. Reading. Okay, reading. I try not to read when I can help it. That's not a good joke. Anyway. Okay, you guys have any other questions from last class that you want to bring up now? No, nothing. All right. Well, if that's the case, we're going to talk more about Bode diagrams in a second, right? We've got the mega homework due on Sunday. You guys should be in a good position to do most of it by now. There's a couple of things that we'll talk about. By the end of class, you should be pretty good to figure out how to do the whole thing. That's the goal, at least. If not, then the start of next class. But definitely look at it, start it, do the parts that you can, come to office hours, ask questions, right? Okay, then we've got exam 3, which hasn't been named yet, and it will. That's going to be a week from Thursday, right? We'll do the same things that we've been doing for exams. It'll just be on test models again, right? If you're normally a Thursday student and you want a place to take it, you can certainly come in here. But make sure you bring your power cord for your computer, because the exam is going to be on test models. The benchmark and the final presentation are due on the 20th, right? So that is the very last Sunday of the semester, the very last day when things can possibly be due. So there's that. So do those things. If you have any questions on the benchmark, let me know. If you have any questions on the presentation, let me know, right? Anything on here, let me know. And we can talk about it, right? Office hours today, tomorrow, from 3 to 5, Friday from 3 to 5. That's PM, not AM, just in case, there was confusion. So swing by, use the link, just pop in. Right. Here's the most up-to-date TriQuizzard standings are here. They have not been updated for Discord yet, but I'll do that later today. We've got the Zoom engineers, Dr. D's sanitizers, zero division uncalibrated calibers, Quizzard lizards in the bag, Michael Scott Paper Company, Doctors Without Doctorates, Life Livers, SDCK, Warzone, Yikes, 185.31, The Swarm Lords, Matilda's, Pointy Compass, and Static Waffles. We've got this week and next week to get points, right? So we'll see what this week holds for the tallying of points. Next week's obviously tied to the exam, just like all exam weeks are. And I will make a YouTube video announcement with who ended up being the winners. And then next semester, I can figure out a way. We can figure out a date and time to exchange trophies for the winners and take a picture. A socially distant picture with everybody with their trophies 6 feet apart. Okay, so let's try this problem, okay? Here is a circuit. It's an RC circuit, right? The input voltage is 2.4 sine omega t volts. I know that my resistance is 4 ohms and my capacitance is 0.003 farads. And I want to use the Bode diagram to find the input frequency omega, where the magnitude of the output voltage E sub C drops to 1.2 volts. Right? So 1/2 of the input. Okay, I mean, so we can certainly do this by hand. Well, first we need a system model, right? If we're going to do a system model, here's our diagram. We've got our current drawn, right? But Dr. D says to always redraw. Apparently, my pen's not going to work today. That's super great. Give me one sec. Please hold. No? All right. Fantastic. This is, give me a second. We're doing this way. We're going old school. Okay, computer. All right, let's see. You guys kind of see that whiteboard, maybe? All right. We redraw our circuit. Right? You guys see that, or is that not good? Is that better?
This way is better.
That is better.
Just moved it.
A bit better.
Is it good focus? Read my handwriting, all those things. All right. So here's our circuit, right? It matches the one that we have here, right? Here's our output voltage, E sub C, right? We know that En is equal to 2.4 sine of omega t, right? So if we want to characterize this, right, we need G of j omega, right? We need the sinusoidal transfer function. If we want the sinusoidal transfer function, we need to get the regular transfer function, right? Which means we need a system model, right? My input being E in, my output being E sub C. All right, we can write down our truths. We've got E sub R equals R IC. We've got I sub C is equal to E C E dot C, right? C E dot C. And we've got KBL, which tells us that EN is equal to ER plus EC. So that's what we've got. And we'll use KBL to get our model. Yeah. All right, hold up. So we use KBL, right? We use our KBL term right here, and we will build our model, right? So let's do that. Let's do that. Okay. So from KBL, we've got EN is equal to ER is RIC, so it's going to be RC E dot C plus E sub C, right? And there we have it, a first order differential equation. Right, a first order differential equation for our model. We'll call it 1, even though there's only one, but it's called 1. And we want the transfer function, right? We want G of S. So you have to take the Laplace transform with 0 initial conditions. So En of S is RCS E sub C of S plus E sub C of S. All right? And we want the transfer function. So G of S is equal to EN, EC over EN of S. One over RCS plus 1. Okay. So we've got the transfer function. Anybody have any questions on where we got this from, right? We take this equation, and I want E sub C, right? So I factor that out. I'm left with RCS plus 1, right? Times EC of S, divide out. I get E sub C of S over EN of S is equal to 1 over RCS plus 1. Now, the nice thing about this is already in the standard form for a first order equation, right? It's already in the standard form for a first order equation. That means that tau has to be RC, right? Because we know that for a first order system, standard form is tau y naught plus y is equal to A U of T. Right? We know R and we know C, so we can figure out the time constant. Remember, for these first order systems, that's important, right? Because tau, 1 over tau, gives us the corner frequency, right? The corner frequency is important because if we go back to last class, the rules by which we draw the asymptotes for our Bode diagram are, low frequency asymptote until we hit the corner frequency that exists at DC gain. Once we hit the corner frequency, we drop off by minus 20 dB per decade, right? Now, we're not going to have to draw this for this, right? Because I told you that if you ever need to pull numbers off of a Bode diagram, right, then we're just going to use MATLAB to do that, right? But we can come up with this, right? And let's look at the problem statement again for a second. Let's do that. It says, use the Bode diagram to find the input frequency where the magnitude is 1/2, right? Is 1.2 volts, which is 1/2 the input. Okay, that's what we're looking for. So I'm going to do this really quick. So let's go back now. Let's go back to this, right? There's my transfer function. And what else do we know about this? Well, we know that we need to find G of J omega, right? And that's just as simple as us dropping in J omega every time we see S. And so there's the sinusoidal transfer function. If we want the magnitude, right, the magnitude of G of J omega, this is going to be 1 over 0.012 times omega J plus 1, right, which is just 1 over the square root of 0.012 omega squared plus 1 squared. And great, right, really good stuff. Why? Well, we don't know omega. We're looking for omega though, right? We're looking for omega. What do I set this equal to? Well, the problem statement said that I want to know when we get to 1.2 volts, right? Well, hopefully that you guys can see this still. Y steady state is equal to the magnitude of G of J omega times the original amplitude, the sine of omega t plus t. In this case, it's not Y though, right? It's really E sub C steady state, right? The steady state voltage drop across my capacitor. And that doesn't really matter because if we look at this equation, if we know that we started with 2.4, but we want the output to be 1.2, then G of J omega has to be 0.5, right? So if we set this whole thing equal to 0.5, we can solve for omega, right? And that's how we would do it by hand, okay? That's how we would do it by hand. We don't need to draw a Bode diagram, right? We can solve for it. But, right, so what does this come out to? What does this come out to? Let me grab my chart. What do we get? if you solve this for omega, what do we get for omega? What'd you get? 5. And your radians are degrees. 1.5. Point 0.12.5 would be 0.06 squared 0.0036. Right, so you have a really large magnitude, right? What's that? Closer, but you're a little bit high. Not 28.3. Anybody at home get something? What do we get? No, Dante, it's not 0.5. The whole thing equals 0.5. You put 0.5 in here, you're going to get a really small denominator, which is going to give you a really large gain. You know that the gain is 0.5, right? How would you solve this, right? If you didn't have a fancy calculator, right? Multiply this up here, right? Square both sides to get rid of the square root. Solve for omega. You end up with 2 answers, right? Because it is a squared term.
I got 144.34.
Correct. That's what it is. 144.34. It's 144.34. Meaning what? Meaning that when we hit the frequency of 144.34, this is where our magnitude will be half. Okay? Now that's not the magnitude in dB. That is the straight magnitude, right? Let's just, so what if I wanted my magnitude in dB? Why would I want my magnitude in dB? I need it in dB so I can compare it to the Bode diagram and see what's going on, right? So magnitude in dB. Remember that the magnitude in decibels is equal to 20 log of my magnitude. In this case, 0.5. And so 20 log 0.5, what's that going to give us?
Really fast, where did that 0.5 come from again?
It was given in the problem statement, right? So let's go back and look. So we use the Bode diagram to find the input frequency omega, right? So instead of before going into the Bode diagram, we're doing it by hand, right? Why? So we can check it to see if what the Bode diagram tells us is true. So we're finding where that input volt or that output voltage drops by 1/2, right? Which means there's a magnitude of 1/2. Why? Because of this equation, right? Because we're trying to drop this input amplitude by 1/2, which means that G of J omega has to be 1/2, right? And we can find out right, if we crunch this, this is going to be a magnitude in decibels of -6.02. dB. That's just taking 20 log of my magnitude, right? And the reason that you need it in decibels is because that's what the magnitude plot is, right? The magnitude plot is in dB. The phase plot is in degrees, not in radians, right? Not in units. So that's how we would do it by hand, right? What if we just were given a Bode plot though, right? What if you just get the transfer function? What if we get the transfer function and we say, you know what, I'm going to type Bode and first I'll create my LTI system and then I'll do Bode, right? Use my Bode command. Hold on, where is it? Here's our Bode diagram. Okay. So what do? Well, first things first, right? We are gonna determine where half magnitude is. What's half magnitude? G of j omega is 0.5 or negative 6.02. And look up here, right? See if this will work, right? It'll give me, whoop. Look right here, right? This is -6 from DC gain, right? This is saying that I have lost 6 dB from my starting point, right? If the DC gain was 10, you would still subtract 6 to find where we've lost half, okay? It's all about where we're starting. It's not about being plus or minus 0, right? Not about being plus or minus 0. So here we are, right? So this is my DC gain, right? I subtract off 6 dB, or 6.02, right? I find where this hits my curve, my Bode plot in the magnitude, and I drop down and I read off my frequency, and it's 144 radians per second, meaning that at 144 radians per second, I will have attenuated half of my input signal, right? There's my corner frequency, 83.33 radians per second. That should be 1 over 0.02, right? 0.12. Sorry. Yep. Right, because remember, omega c is 1 over tau. Our DC gain was 1. How did we know that? How did we know DC gain was 1? You come back to your transfer function, you plug in zeros for your s's. What we're left with is 1 over 1. See how Sorry about the earthquake test, everybody. 1 over 1, DC gain of 1. 20 log 1 is 0, right? 0 dB indicates that we didn't lose, but we also didn't gain any signal, right? We didn't attenuate, but we also didn't amplify.
Did you say there was a way we could use natural log?
No.
2 classes ago, I think it was.
No, I said that you can't use natural log. Make sure that you're using log base 10.
Okay, you can't put natural log to the right base, right? Because base E.
No, because that's base E.
Yeah.
Right? And that's going to throw everything off.
Thank you.
We watch the video later. It actually talks a little bit more about how decibels came to be and why we use log base 10. Okay. Right, so the output voltage E sub C is reduced by 1/2 magnitude at the input frequency of 144 radians per second, or 23 hertz, right? So there's a couple of things that we're going to talk about later when we get to second order systems concerning bandwidth and resonance, right? But for an electrical system, right? Maybe this is good, maybe this is bad. I don't know, right? Depends on how much output voltage you need, right? If you're good to have 1.2 volts amplitude at that frequency, then we're all set, right? If you need more, you've got to run it at a lower frequency. If you want less, you've got to run it at higher frequency, right? Because that's the other thing we can tell from Bode plots, right? I will get less signal the higher my frequency is here, right? If I increase this from 144 to 1,000 radians per second, right? Now, well, let's give me a pointer. No, none of that. Now, this point right here is minus 20 dB, right? I've lost a significant portion of signal, right? I have basically no voltage coming out here anymore, which is probably not what you want, right? Probably not what you want. Okay. So this is a common design for a low pass filter. Right? So things with low frequency will get through, things with high frequency will be attenuated. Right? Why do we want low pass filters? I'll show you an example of why we want low pass filter in a second. But first, are there any questions about this, right? What's the expectation here, right? The expectation is that if you're given a Bode diagram, you should be able to get this information off of it, right? You can be told, I want, it's very common for a system design to say, you know what, I need to know, when this passes 6 dB, right? Because everything beyond that, the data is corrupted, right? Or, I'm not interested in high frequency noise being propagated through my system, so I'm going to filter it out, right? I'm going to let the low frequency stuff in, but I'm going to filter out the high frequency stuff, right? So if you're told from design parameters that you are good, you want to know when you attenuate, 3/4 of your signal, half of your signal, right? That's telling you what gain, right? That's telling you what magnitude that they want to apply. And you can convert that to dB, get the Bode plot out, find where that is below your DC gain, right? Find the frequency at that point. So here's that same circuit that we just talked about, right? So, all right, I guess before we go on, right? Are there any questions? Does anybody have anything they want to ask? Everybody okay? No. Okay. All right, so this is going to be a little bit different. So it's the same circuit, same system, right, that we're just using. I've got the same parameters, but this time my input voltage is E sub S, which is 2.4 sine 10t, and E sub n, right? So E sub S, we're going to call that the signal. And E sub n, we're going to say that's the noise. And the noise is a distinct signal that happens here at 800 radians per second. So it's a high frequency noise signal, right? 0.2 sine 800 t. So really low level humming, right? Really low level humming. Okay. So now we've got this composite signal, right? So how are we going to handle this? Well, I think that most of us know from taking instrumentation that noise is really a pain, right? And most of the time we want to get rid of this noise, right? We want to attenuate the noise, but we want to keep the signal, right? Because you can't throw the baby out with the bathwater, right? So how do we do that? Right? Well, if you wanted to build this in Simulink, you could. You use something that looks like this, right? So I've got a sine wave input at 2.4 times sine 10t. I've got a sine wave noise signal of 0.2 sine 800. I add the two together with my summing junction, right? Here's my summing junction, add the both of them together. And you can bring these out to workspace if you want, right? But notice, you can plot, so this is why I'm bringing these out to workspace. First of all, I want to plot just the input signal without the noise, right? Second, I want to plot both of them together, right? Added together, that's EN, right? That's that to workspace 2. There's my transfer function, right? For my, what we call the RC low pass filter, right? And then finally, I bring out to workspace the output signal, right? Just E sub C. Okay. So what happens? What happens if you run through this, right? What do you think happens here? What do you guys think happens? Based on what you saw from the Bode plot for this transfer function, which is not going to change. Based on this Bode plot, what do you think happens to this signal? Based on this Bode plot and what you know about the term low pass filter, what do you think happens?
All the high pass frequencies are going to be cut off.
Yeah, we're gonna attenuate the noise, right? That's the goal. Is we want to get rid of the noise, and hopefully we'll be left with everything underneath that. Everything that's less than 800 radians per second, right? So let's take a look, right? So here's my diagram, and here's what I've got, right? So I've got on the top, that's my signal plus, right? That's the signal and E in, right? So E sub S is the dashed line, which you can't really see here, but the noise is what's on the top plot is what is dominating our response, right? And if we zoom in on this block over here, you'll see that you've got this noisy signal that's overlaying this nice smooth dashed line, right? So this is the combined input signal, right? This is E in, right, where we've got our desired signal that's hidden by this noise, right? And this is before we go through the low pass filter. Once we go through the low pass filter, this is what we're left with. So E sub S is the solid line and output is E sub C. So we've got, right, so we've stripped out the noise, right? And we're left with this signal that's pretty clean. It's just shifted, right? It's just phase shifted. The magnitude stayed basically the same, but we've phase shifted. Okay. So what, right? This is an example of superposition again, right? Because look what happens here. At 10 radians per second, right? 10 to the 1, which is right here, we are at 0 dB. So we have no change in amplitude. The magnitude does not change. 0 dB is a magnitude of 1. But we do have a phase shift of what looks to be about, right? So if you look right here, I'd say that that's like maybe 5-ish degrees, -5 degrees, right? So we've got a lag of about 5 degrees here. Right. What about 800? Well, here's 100, 200, 300, 400, 500, 600, 700, 800. We're at about -20 dB at 800. All right, so what magnitude is that, right? -20 dB, right? So that is So that's about 0.1. And how did I come up with that? Give me a second. So I clear this board. We'll talk about it. Remember, in dB is 20 log G of J omega, right? But I want this, and I have it in dB already. So what do I do? Well, this becomes 1/20th G of J omega dB is equal to the log of G of J omega. Well, how do I get rid of log? 10 to the G of J omega in dB divided by 20 is equal to G of J. Right? Put everything to the, I take 10 to the power of everything. Okay? It's a 10. It's hard to see because of the glare. We know this, right? We said that that's about -20. So 10 to the -1.1. So we've lost 90% of our signal. Right, we've attenuated by 90% at 800 omega. Right? What about phase? Well, it doesn't matter because it's so small that it's basically not there, right? Okay. I guess I didn't have to go all the way back. I forgot that I put it right there. And so here it is again, right? The same Bode diagram, same system, right? So the thing to remember is that the Bode diagram doesn't change if you're using the same transfer function. Doesn't matter what your input is. The Bode diagram is for the transfer function, right? So your input can be anything, and even when we don't specifically ask for the frequency response of something, right? We can still find the Bode diagram, right? As long as you have a transfer function and you have access to MATLAB, the Bode command will do it for you. You can also draw them, right? And we started to talk about how we would draw them. Remember, just as it's hard without the pen here, right? But remember, low frequency asymptote at DC gain, which we determined was going to be 0 dB, right? Here's my corner frequency, 83.33, which is 1, 2, 3, so 10, 20, 30, 40, 50, 60, 70, 80, right? Somewhere in here. And then we have our high frequency asymptote at -20 dB per decade. Right? Notice the purple lines here. On this particular one are our frequencies that we are doing 10 and 800, right? And you can read off where our magnitude and where our phase is. And we've been phase shifted about 80 degrees in the 800 radians per second noise case. Okay. Any questions? And so that's the use, those are the uses of Bode diagrams, right? We can use them to pick off the steady state response at a given input. We can use what we know about a given magnitude to find the frequency where that would happen. We can even investigate how much attenuation we would expect to get out of a system. Okay. Questions? No? Comments, concerns? Yeah. Yeah, shown. The phase equation? Yeah. So what is the phase equation? Let me clear this off for a second. We're not. For this particular example, G of j omega was 1 over 0.012 omega j plus 1, right? That's what we got. So if you wanted, we talked about how to do magnitude. How do we do the phase, right? Well, that's the argument of this, right? But what that boils down to is remember what we're seeing here. If you draw everything on the real imaginary plane, right? You draw everything on the real imaginary plane. Each one of these is a vector in the real imaginary plane, right? So the numerator is just 1, and 1 is completely real, right? So we'll call this, this blue line here is our numerator. The denominator has a slight, this is not drawn to scale, but this is going to be we've got some imaginary component and some real component, right? And we want the total magnitude of these two vectors, right? So the magnitude of these two vectors, right? The total magnitude is just 1 divided by the other, right? We use Pythagorean theorem there where, this angle, we'll call that angle phi. Right? Each one has a phi, right? We'll call this phi for the denominator, sub d, and this has phi sub n, right? But phi sub n is 0. And we can clearly see that from here, right? So if we wanted to calculate the total phase of this, we can call it phi sub t. This is equal to phi of the numerator minus the phi from the denominator. Okay. Why is it that? Well, remember in polar form, this is actually ye to the j phi numerator divided by u e to the j phi denominator. Okay. And if you wanted just the phi terms, well, because it's an exponent and you're dividing them, that's the same as these two things saying e j to the phi n minus phi sub d. Right? And you can't hardly see that up there, but that's what it says. That's something from last class that we went over as well. So anyway, so I want this total phase angle. Well, kind of know that this one's 0 already, but why is it 0? Well, because if you use this triangle here, right, this is tan inverse of the imaginary portion, which is 0 divided by 1, which is the real portion. Phi sub d is the tan inverse. Well, tangent is opposite over adjacent, right? So the imaginary portion, 0.012 omega, divided by the real, which was 1. And that's how you would get the phase. Then you plug in whatever omega you have, right? You plug in whatever omega you have. Okay. Any other questions? We're in a cruise zone. Talk more about Bode diagrams, right? Because first order are nice, but you know, as we discovered, second order is often more interesting. Right, so suppose we have a second order transfer function like this one, right? And it's written in standard form again, because why? Because remember, when you write it in standard form, you're left with this K on the top, which is our DC gain, right? Do you need to write it in standard form? No, you don't. You don't have to, right? But it helps with getting our DC gain, right? So if we set K is equal to 1, omega n is equal to 10, and zeta is equal to 0.2, right? We plug those things in here. We'll get 100 over s squared plus 4s plus 100, where our DC gain is 1, right? How do we find that? Well, again, just substitute in 0 for all your s's, right? And whatever's left is the DC gain. Why is that the DC gain? Because at steady state, we don't have any more time derivatives, so the s terms go away. They become 0. And we're left with 100 over 100 or 1. All right. So that DC gain stuff that we learned, you know, a month and a half ago, right, came back. Okay. Okay. So we've got some rules. We've got some rules here, right? So just like last time, we're gonna have is that my microphone? Do I sound weird now?
You were just muted for a second.
Is it good now? All right. Okay. All right, so I've got a flat, low frequency asymptote that exists with a magnitude of 20 log 10 kdB, right? So you take the DC gain and you convert it to decibels, right? That's our flat low frequency asymptote. We also have a high frequency asymptote, but this time, because we have a second order system, it's minus 40 dB per decade. Anytime you add an order to your system, you're adding an additional attenuation of 20 dB per decade, right? So first order was 20, second order is 40, third order is 60, so on and so forth, right? We're not going to do any hand drawing of Bode diagrams higher than second order in this class. We're just not. Right, so I've got high frequency asymptote. Where does that start? Great question. It starts at the corner frequency, which is equal to the natural frequency in this case. And so last time, for first order system, it was 1 over tau. This time, it's just omega n. Your natural frequency is your corner frequency. The peak magnitude increases as the damping ratio zeta decreases. You'll see what that means in a second. Right, so rules 1 through 4. Rules 1 through 4 apply to the magnitude portion of the plot. 5 through 7 are all about phase. Right, so remember, we started at 0 and went to minus 90 for first order. For second order, we start at 0 and we go to minus 180. Guess what? For third order, we would go to minus 270, right? You just keep adding an extra 90, negative 90 of phase. Sometimes MATLAB will do really fun things where it plots it, instead of plotting it from 0, it will start it at 90 and go to minus 90. Which is the same thing as a net loss of minus 180, right? So just be aware that that's a thing that can and will happen. All right. The phase angle shows a sharper transition from 0 to minus 180 as the damping ratio decreases. So as zeta gets closer to 0, right, as we have less and less damping, we are going to have a sharper transition in our phase. Right? We'll talk more about that in a minute. And the phase angle of minus 90 is where our corner frequency is going to cross at our corner frequency, right? So just like before, we're halfway through our phase at the corner frequency, right? We're halfway we're at minus 45 in the first order and minus 90 here, okay? So them's the rules, right? Them's the rules. Okay. Any questions on the rules here? Right, so seems like it's a big checklist, right? But the things that we need to remember are there's the real things, right, for magnitude are the first three, right? Flat, low frequency, right? They're the same rules. They're the same rules as for first order, right? You have a flat, low frequency asymptote at DC gain. You have a high frequency asymptote that you lose minus 40 dB per decade, and you've got they meet at the corner frequency, right? Which in this case is just omega n. It's a little bit easier to remember for second order because if you can find the natural frequency, you've already found the corner frequency, which is why writing it in standard form is nice. Because by writing it in standard form, you already know what omega n squared is, right? Okay. Then phase just goes from 0 to minus n, right? And it crosses minus 90 at omega n. So let's run through one. Let's take a look. Okay. Oh, no, I didn't want to do that. Now we're good. So for the system that we were, gotta stop doing that. For the system that we were discussing, right, which was 100 over s squared plus 4s plus 100. We have a low frequency asymptote at the DC gain, right, which was a DC gain of 1, which translates to 0 dB. 0 dB, right, and so that's the top part of the dashed line there. At omega n is equal to 10 radians per second. That's our corner frequency. We're going to draw our asymptote, and that is going to drop by minus 40 dB per decade from there, right? But remember, this is the asymptote, right? This is the asymptote. So this is just showing us the limits, right? The way that this actually looks is there's going to be some peak around omega n, and then it's going to drop off. How high is that peak? That depends on our damping ratio, right? Because that was the rule right here, right? The peak magnitude increases as damping ratio decreases. What does that mean? That means as zeta goes down, as we get closer to no damping, we get larger and larger peaks here, right? That means that as zeta increases, we will be forcing our system to have a lower and lower peak, right? So the more damping we put in, the less overshoot, right? The less magnitude you get. As we increase our damping ratio zeta, this peak right here will start to smooth out and will start to follow this asymptote more closely. And then it will start to look like a first order system because it will be over damped once it gets over 1, right? Zeta greater than 1 looks like a first order system. Underdamped gives this, right? And what is this Bode plot specifically telling us, right? This is saying that as frequency increases, I'm going to have a spike. I'm going to have an amplification, right? And then I'm going to start to attenuate at some point, right? When do I start to cross 0? All right, it looks like about 15-ish radians per second right here. So that crosses 0. So we're going to start to attenuate after that point. What about our phase? Well, our phase goes from 0 to minus 180 at 10 here, which was our omega n, our omega c, crosses minus 90. Right? So that's the asymptote method, right? So if you're asked to draw a Bode plot using the asymptote method, this is what they're asking for. Not even asking you to fill in what the Bode plot actually looks like. It's really just draw the asymptotes. Because this gives us a good idea of how this is supposed to behave, right? Okay. Do we have any other questions? Anybody? Are you okay following? All right, no questions. So how does zeta affect this, right? And here it is. Here's another plot, right? This is the same transfer function that we just had, but we've changed zeta ranging from 0.1 up to 0.9 in increments of 0.2, right? So as zeta increases, so if we look at the magnitude, right, looking up here. Oh, sorry. As zeta increases, we get a flatter and flatter curve, right? So this is zeta of 0.1, 0.3, 0.5, 0.7, and 0.9. And you can see that flattens out. For phase, as zeta increases, right? As zeta increases, I get a flatter transition, right? Notice that at zeta is equal to 0.1, this is a very sharp transition up on the top, right? That top curve comes over and quickly changes phase, right? It basically stays fairly constant for a long time, and then it sharply changes, right? Yeah.
So as it's getting closer to the more, I guess, bell curve line that we increase in data.
Yes. So way of thinking about this is for higher damping ratios, you will be able to maintain phase for higher frequencies, right? But once you change, you're going to change, and you're going to change very quickly. For low damping ratios, right, or sorry, for high damping ratios, you will change phase at a much more constant rate, right? For low damping ratios, we're going to change phase rapidly. Remember, second order system, the corner frequency is omega n. It's a big one. Now, we've all seen what happens, right? And we'll get to it in vibrations a little bit, right? Well, you know, I'll just hang on until we get to vibrations. For that. Okay. So this is how changing the damping ratio affects our system, right? And so these are the design trade-offs that we talk about in the frequency domain, right? Can you have a low damping ratio? Is it okay for this peak to exist, right? Well, the answer is it depends on what's our operating frequency, right? Depends on what our operating frequency is. Right, so for high frequencies, we still attenuate roughly by the same amount, right? If you go out to 100 radians per second here, right, all the way to the edge, all of these curves are basically at minus 40 dB, right? So at a certain point, they all catch up to each other, right? So the trade-off is, are you expecting this to be running at 10 radians per second, right? Because if you are, then you have to investigate whether or not your system can handle an amplification of your signal by about 15 dB, right? Which is depends on what it is, right? All right, so to recap, right, a flat low frequency asymptote exists at the DC gain in decibels. The high frequency asymptote exists with a slope of minus 40 dB per decade. Those two things meet at the corner frequency, right? Which is the natural frequency. The peak magnitude increases as zeta decreases. The phase angle starts at 0 and asymptotically approaches minus 180 at high frequency. Phase angle shows a sharper transition between 0 and minus 180 as the damping ratio is decreased. And the phase angle phi is equal to minus 90 when we hit omega n. So we're going to talk about some performance parameters and why they're important. And so that's how we draw a Bode diagram for a second order system. But what can we take away from a Bode diagram for a second order system? We can talk about the idea of a resonant frequency. Right? And I think you've probably heard the term resonant frequency, or when something resonates before. But when the input frequency is near the corner frequency, the magnitude depends on the damping ratio, right? And we showed how this changes, right? As zeta approaches 0 with no damping, then the magnitude becomes infinite when our input frequency matches the undamped natural frequency. And therefore we have resonance. Okay? So that peak amplitude that we saw, that is the resonant frequency. The resonant frequency is the highest frequency, right, that we are going to see. I'm sorry, is the frequency at which we see our highest magnitude, not the highest frequency. That doesn't make sense. Right, so as damping ratio increases, the resonant peak on the magnitude decreases. Right, so if we want the amplitude ratio, we want to find when the amplitude ratio is at its maximum, we need to find the resonant frequency. What is the resonant frequency? So omega r is equal to omega n times the square root of 1 minus 2 zeta squared. When we have no damping, the natural frequency is equal to the resonant frequency. The resonant frequency is always less than or equal to omega n. It will never be larger. I mean, look at the equation. There's no possible way it should be larger. The only way that it could be larger is if you get a negative zeta, which is physically impossible. So there's that. And if zeta is equal to 0.7071, there's no peak resonant frequency. The magic number. What's the significance of that number is that you end up with 45 degrees on the real imaginary plane. Okay. All right, so resonant frequency is the frequency where we have the highest magnitude. Okay, that's the important definition that we want to take away. What is the resonant frequency? It is the frequency at which we have the largest amplitude in our system, right? The largest magnitude. What affects that magnitude? Zeta, right? Zeta affects that magnitude. We just showed that. So that's resonant frequency. Okay. We can also talk about cutoff frequency or bandwidth. So bandwidth is one of those other terms that we throw around quite a lot, right? I don't have the bandwidth to do this, right? We use it colloquially quite a bit, right? But what is it from an engineering point of view? Well, in order to talk about bandwidth, we need to talk about cutoff frequency. And we define the cutoff frequency to be the maximum input frequency at which the output of the system will track the input sinusoid in a satisfactory manner. Okay. So think about it this way, right? There is some frequency that we are going to say anything beyond this point, we no longer get the fidelity of signal that we want, right? We're good with losing X amount of signal, right? But anything beyond this point, That's going to be my bandwidth, right? I'm cutting it off after that. I don't want anything past this, right? So typically we say that satisfactory tracking includes all frequency up to the point where the amplitude ratio is reduced by a factor of 0.7071. In dB, that's a 3 dB drop. Right? So what is it? That's a 71% drop, right? Or 30% drop, right? We're saying that we're good with losing no more than 30% of our signal, right? That's what we're saying. That's a 3 dB drop. So how do we, so the bandwidth is read directly from the Bode diagram with these two steps, right? So the bandwidth is a range of frequencies, right? It's the width. The bandwidth is a range of frequencies ranging from typically 0 to omega R, which is my resonant, or I'm sorry, omega B, which is my cutoff frequency. Not to be confused with omega C, which is my corner frequency. All right. So typically what we do is we read the low frequency magnitude on the Bode diagram in dB, and we read a frequency where the magnitude drops 3 dB below that. And then we just find where that intersects our curve and take that as our omega B, right? So you have to have a Bode diagram to find bandwidth, right? You have to. Well, I guess you don't technically have to. I mean, you could go through it by hand and figure out where you drop from DC gain by 3 dB, right? Figure out what your magnitude was and convert it to decibel, and then solve for omega. Yeah, sure.
So if we be setting the U omega W to 0.7071 or 0.2.
So if you're going to do this by hand, you set it to 0.7071, which is 3 decibels in once we convert it back from decibels. So let's take a look, right? I think it's a little bit clearer when we have an example, right? So here's I've got this system. This is a DC gain of negative 36.3. Okay, so it already starts off attenuating significantly. I'm going to subtract 3 from that DC gain, right? Which brings me down to 39.3, negative 39.3. I draw a line at negative 39.3. I see where my Bode diagram for magnitude intersects that. I drop down. I can read off the frequency. My bandwidth is between 0 and 27 radians per second. Okay, that's what my bandwidth is. So, yeah, Sean.
39.3 arbitrary spot, or
It is based off of the 36.3. It's 3 dB less than my DC gain. Right? So find your DC gain, subtract 3, find where that magnitude intersects. Right? So what if, and this is where not having the pen hurts it a little bit, right? So I'm gonna try drawing something really quick. What if I had a funky Oh, it doesn't feel like good either. What if I had a funky looking Bode diagram that had like a double peak, something like this? And with this would be a really significantly higher order system than a second, right? Maybe it's a 4th order system. So I have 2 peaks, one that's at a lower frequency, one that's at a higher frequency, right? But I've got these 2 peaks, and if I had drawn this appropriately, right, let's just assume for a second that this peak actually dips below here, right? And this is 3 That's my minus 3 dB, right? If I started at 0, we'll say it starts at 0 just for the sake of the math, right? That's 0 dB up here. Right? So I dropped my 3 dB and I want to read my bandwidth off, right? I've got 2 segments for bandwidth here. I drop below 3 dB here, right? So I've got bandwidth from omega 1, omega to omega 2. And I've got bandwidth in this portion here, right? I've got omega 3 is less than omega 4, right? I just 1, 2, 3. Okay. So if you get funky higher order systems and you want to get the bandwidth, it doesn't have to be a single range, right? There are multiple sets of operating frequencies in which we meet the criteria for this bandwidth, right? Why would this happen in the real world? Again, if you had a 4th order system, right, it's identified by 2 second order equations. So you're going to have a low frequency second order spike and a high frequency second order spike. But like I said, in this class, we're only going to really worry about second orders, right? But if you saw something, right, that looked like this, you have to identify all the regions that, as bandwidth, that are above that minus 3 dB from the BCD. Okay. Bandwidth lets us know what operating frequencies we can be in such that we do not lose significant portion of our input signal. For those of you who like to game, right, how does bandwidth affect your gaming, right? Well, if you have too many devices on your system and you force your bandwidth, right, then you start to see lag, right? And depending on what game you play, that could be good for you or it could be very bad for you, right? So there's that. Okay. Questions on bandwidth or resonance. Is resonance good? Is resonance bad? Right? Depends on your application. Typically, as mechanical and biomedical engineers, right, you are going to want to minimize the amount of vibration in a system, right? You're going to minimize your high frequency noise. Electrical engineers like sometimes in certain applications like to have this large spike, this large amplification. Excuse me. The cutoff frequency is omega B 27 per second, excuse me, or 4.3 hertz. So our bandwidth is 0, right? And so we define bandwidth as a range of frequencies. The range of frequencies that we can operate in such that we don't drop below 3 dB attenuation. Where does that 3 dB come from? That is a standard. It is somewhat arbitrary. Some, depending on where you work or who you talk to, some people are okay. Some applications you can lose more than that, some less, right? Depends on what we're doing. So we can do this in MATLAB. Okay, so we can do this in MATLAB. So how do we build the Bode diagram in MATLAB? We'll do it the same way, right? We talked about this a little bit for first orders, but for second order systems, the process is the same. First thing we do is we create our LTI system, right? In this case, we're setting numerator and denominator. Notice I skipped the TF function here, right? I skipped the TF function. Bode will automatically convert your numerator and denominator terms into a transfer function if given in this format, right? So notice we can, if we just wanted the Bode diagram, that's fine. Or we can compute the magnitude and phase at a specific input frequency, right? So you set your numerator, you set your denominator, you set your omega. In this case, they used W. We set that at 10. And then you use the command mag phase equal Bode, right? Because this will return you the mag and phase for this Bode diagram at omega. And then there's the conversion factor, mag dB is equal to 20 log 10 of mag. Log 10 is the log base 10 operator in MATLAB. Finally, you can do this with state space, right? The same way. Bode takes in both state space and transfer functions. Right. Excuse me. As long as you give it A, B, C, and D. So we can do quick checks at specific frequencies to make sure that we are doing things correctly, right? Again, just a reminder, in the homework, certain problems say to do things by hand and then check with MATLAB. If you are asked to check with MATLAB, please provide evidence that MATLAB was used to check. Don't just say, I checked it with MATLAB and leave it like that. Okay. All right. So that's how we do it with MATLAB, right? Not too bad with MATLAB. Pretty straightforward, right? It has built-in commands. You don't really have to do much with it. So let's watch a video.
Welcome back to Control System Lectures. As always, if you have any questions or comments on what I'm about to say, please leave it in the comment section below and I'll address it. In this lecture, I want to present an introduction to frequency response methods, and in particular, I'm going to describe the Bode plot, how it's generated and used to visualize the frequency response of a system across the entire spectrum. I want to start by explaining another benefit of an LTI system. If you design a linear time invariant system, then there's only a limited number of mathematical operations that you can use. When building an LTI system, you can only use: one is multiplication by a constant, the second is differentiation of the input signal, the third is integration of the input signal, and the fourth is adding two inputs together. Now you can always do division by multiplying by the reciprocal, and you can also subtract by adding a negative number. You might be wondering why it's important for me to start this lecture this way, and why bring up the fact that a linear system can only consist of these 6 operations. The answer is that when you subject a sinusoid to these operations, it doesn't change shape. And part of not changing shape means that it also won't change frequency. A sine wave input will always generate a sine wave output of the same frequency. In fact, the only 2 differences possible between an input sine wave and the output sine wave that's generated is the amplitude, which is the height of the sine wave, and the phase, that is, shifting the sine wave in time. In fact, the sine wave is the only repeating waveform that doesn't change shape in a linear system. You can see here graphically what it means to change in amplitude and also to shift in phase. Let me give you a quick example so you can see what I mean. If we take an input sine wave and subject it to these 2 separate paths, the upper path is just multiplying it by a constant 2, and the lower path is integrating it, and then summing them together produces the output. If we make the input a pure sine wave of frequency 1/2 radians per second, then we could just calculate mathematically what the output would be. I'd like to make a quick note about frequency. I'm going to refer to frequency in units of radians per second, but this is proportional to hertz. So you can use either in this example. All right, back to solving this mathematically. The output would then be the upper path, which is a gain of 2 times the input, plus the integral of the input with respect to time. We can simplify this further by just taking the integral in the second half of the equation. Now, in order to interpret this from here, we're going to need some help from some trig identities. Now, I didn't remember this. I had to actually go look this up. But this trig identity that I'm going to be using is a sine of x plus b cosine of x equals the square root of a squared plus b squared times the sine of x plus rho, where rho is equal to the arctangent of b over a. Now, of course, this is only true if a is greater than or equal to 0. So let's apply this trig identity to our problem. In our case, a is equal to 2 and b is equal to -2. So the change in amplitude of the sine wave is just the square root of 2 squared plus 2 squared is the square root of 8 times the sine of 1/2 t plus the arctangent of 2 over -2, which is the arctangent of -1. If we write this in decimal format, this is just equal to 2.83 times the sine of 1/2 t minus 0.785 radians. Now, it should be obvious from this example that the sine wave that we input into the system is still a sine wave on the output. However, the amplitude has increased from 1 in the original input to 2.83. That's the change in amplitude. And the phase has been shifted by 0.785 radians. Notice also that the output has the same frequency as the input, which is 1/2 radians per second. Now you could draw the input and the output in the time domain, and it would look something similar to the graph that we've done above. And that would work if you were only concerned with the response to a single frequency. However, more often than not, you're going to be interested in the whole frequency spectrum. So how can you visualize the gain and phase shift across the entire spectrum? Well, one way to do that is with the Bode plot. The Bode plot allows frequency response information to be displayed graphically on 2 separate plots, one for gain and one for phase, both of which are plotted against frequency on a logarithmic horizontal axis. But there's a caveat to plotting amplitude gain on a Bode diagram. We don't just plot the magnitude of the gain directly. First, we have to convert it into power, and then we represent the power gain in decibels, which is a logarithmic unit. To convert the amplitude to decibels, you first take the log base 10 of the ratio of amplitudes and then multiply it by 20. If you're confused about where this equation came from, let me just give you a quick history on decibels. When Bell Telephone Laboratories was trying to quantify loss in audio levels through telephone circuits in the early 20th century, they needed a unit of measurement and one that could cover a large range of audio power differences. Because the ear responds to sound pressure logarithmically, using a logarithmic scale corresponds to the way humans perceive sound. They created a measurement called the transmission unit, TU, where 1 TU equaled 10 times the log base 10 of the power loss, and this was chosen because it approximately was the smallest power attenuation detectable to the average listener. Now, to honor Bell Labs founder Alexander Graham Bell, they later changed transmission unit to decibel, or 1/10 of a bell, where bell is just the log base 10 of the power ratio. So to get from bells to decibels, you have to multiply by 10. Also note that power in a sine wave is proportional to the square of the amplitude of the sine wave. So now we can write the decibel equation with respect to amplitude squared, which is 10 log base 10 of the amplitude squared. And just because of the properties of logarithms, the exponential 2 just becomes multiplication, and you get 2 times 10, which is 20. So let's get back to plotting on the Bode plot. If we convert the gain from amplitude into decibels, we can plot the gain for that frequency omega. And for omega of 1/2, we can calculate the gain to be approximately 9 decibels. So on our gain plot, we could find where 9 decibels would be on the vertical axis, and where 0.5 radians per second would be on the horizontal axis, and put a little x there. You can do the same for frequency, but you first have to convert 0.785 radians into degrees, because it's traditionally shown in degrees, and that's -45. This is the frequency response for a single sine wave. But remember, we're interested in plotting the gain and phase across the entire spectrum. So instead of running through the example above an infinite number of times, each at a different frequency, we could have just set it to a variable like omega and solved the system for any frequency. So if we had done that and we had a lot of time, we could have plotted a gain and phase plot that looks something like this for our particular system. And with the exception of being time-consuming, for this simple example, solving the response to the sine wave input was relatively straightforward. Well, except for having to remember that crazy trigonomic identity from earlier. There is a way of solving this without having to remember those identities and still produce the same relationship with frequency, and that's by referring to the system's transfer function. If we take the Laplace transform of the system above, the gain of 2 stays at 2, and the integral becomes 1 over s. Now writing the transfer function for a system like this can be done. The output y of t is equal to 2 times the input u of t plus u of t divided by s. A few algebraic steps here and you can solve for y of t over u of t, which is the transfer function, which is equal to 2s plus 1 divided by s. Recall that the Laplace transform s is a complex variable, sigma plus j omega. However, when we're talking about frequency response of a system, we are talking about the steady state response. That is, once all the transients have died out, or in other words, when the exponential term sigma is 0. So for steady state behavior, s just becomes j omega. Steady state phase and gain can be calculated directly from a transfer function by setting s to j omega. That makes the transfer function become 2 plus 1 over omega j, where 2 is the real component and 1 over omega is the imaginary component. If we then plotted these real and imaginary components on a real and imaginary axis, then we can calculate gain and phase geometrically from this plot. So here our real component is 2, and for omega of 1/2 from our example above, 1 over omega would also be, well, it's negative 2. I'm sorry, I made a mistake here. This 2 plus 1 over omega should actually be a minus because j times j is negative 1. So it's negative 2 on the imaginary axis for omega of 0.5. And if we draw a line from the origin of the axis to that point, then the length of the line is the gain of the system. And the length can be calculated by just taking the square root of the real component squared plus the imaginary component squared. This is just the Pythagorean theorem. And the phase is the angle between that line and the positive real line. And you can solve for this using the arctangent. I'm using arctangent 2 in this case only because it keeps track of the sign of the inputs, and so you don't have to worry about whether A is positive or negative like we did up above. So again, the length of this line is the gain, and the angle off the positive real line is the phase. So you can see in this example that the real component doesn't change with frequency, only the imaginary component. And if we sweep through frequencies from near 0 all the way up to near infinity, you can get a visual understanding of what the gain and the phase are doing for this particular system. At omega of near 0, the imaginary component is almost infinite. And at an omega of near infinity, the imaginary component is near 0. And if you drew that red line from the origin, starting with omega of 0 down at near infinity, which would be a near vertical line, infinitely long, you would see that they would get shorter and shorter and shorter and shorter, and finally ending with a length 2. If we go back up to our plot, you can see that's exactly what the gain is doing. The limit as frequency approaches infinity goes to 6 dB, which is a gain of 2. And off to the left, as frequency approaches 0, the gain goes off to infinity. Also, if you look at phase here, you can see that phase starts out at negative 90 degrees and then goes to 0 degrees. And again, that's exactly what our plot is doing. And that's how you can represent a large amount of frequency response data through a system. In fact, that's exactly how graphing programs such as MATLAB would calculate the Bode plot from a transfer function. Doing this by hand, though, still seems like it would take a long time. But luckily, there is yet another way to graph the frequency response across the spectrum. And not only is this a much faster way, but it also gives you an intuitive understanding into the frequency response of the system, and you do this only by looking at the transfer function. By following a few rules of thumb, you can graph the Bode plot by hand using straight line representations, and I'll show you that in the next video. For now, as always, thanks again for watching, and don't forget to subscribe.
I think you're still muted, Dr. D.
No, I'm not. You're muted. All right, we're gonna watch one more later. We'll come back to that one, but I want to get into vibration first, right? That first video brings us up through kind of the history of Bode plots and brought us up through how that steady state and why that steady state equation works, right? We'll watch the second part of that in a little while, right? But let's get into vibrations, right? So vibrations. Vibration in a mechanical system is typically an undesirable phenomenon, right? Typically, we don't want vibrations, but why? Why? Why do we consider vibrations to be bad? Anybody?
Don't they lower the overall efficiency of the system?
Sorry, Jackie, say that one more time. You kept broke up.
Don't they lower the system?
Yeah, I missed the second part. Sorry. It can lower the efficiency of the system. Right, that's one thing that can happen. Right, you are if you're vibrating, you could be losing certain aspects that you would normally lose. Right. What are some other things?
Can't failure of physical system.
Sorry, say that one more time.
Which one of us?
Either one. Jaleese, go.
That it can sometimes destroy a physical system.
Distort the system, sure. Scott?
It can cause failure.
It can cause failure, yeah, right? We can have fatigue failure. Right? This is a loading cycle, right? So it can certainly cause fatigue, right? We've got fatigue, we've got screws backing out, right? Vibration, everybody's seen that, right? You vibrate something hard enough, screws will back out. Heck, the electromechanical system, right? We can't run this one too long because I should have used the left-handed thread on the one, but that's fine, it's cool, it works anyway. Right? Noise, general noise in the system, right? Fatigue cracking, crack propagation, all those things. Suspension systems are used to isolate a body from vibrations and or damp out transmitted vibrations, right? So the two flavors of vibration isolation systems that we have are one, it will reduce the transmission of vibrations from a machine to the environment. So I have this machine that I know vibrates quite a bit, and I don't want the rest of the machine shop to vibrate around it. So I'm going to build a system to isolate, to damp out those vibrations before they get into the world. Or you want to reduce the transmission of vibrations from the environment to a machine, right? Or, for example, the scanning electron microscope, right? We want to build, one of the capstone projects is to build a vibration reducing table so that it doesn't vibrate, right? Because we want the SEM to be really still, right? When we're taking our measurements, right? We want to reduce all of that noise. Okay. So we're going to focus mostly on vibration isolation. Okay. So here's a vibration isolation system, right? These vibration mounts that are on the bottom are essentially just spring damper systems, right? Spring mass damper systems. And notice, right, we'll have the base motion would be our input here, X sub B. We have some input vibration, and we want to attenuate as much of that vibration as possible for high frequencies, right? Presumably, right? That's the way that your car suspension works, right? And I know I brought it up last class, and I'll bring it up again, but it's why you don't feel every little groove in the asphalt, right? Because that's high frequency noise, but also why when you hit like a speed bump, that feels so bad, because that's low frequency noise, right? Yeah. So the goal is to reduce the transmission of the base motion to the instrument in this case. The reverse is also true, right? We can do this in reverse, and we can say that we want to reduce the amount of transmission of vibration from our machine to the area around it. This brings up the idea of transmissibility. And what is transmissibility? It's the measure of how good we are at suppressing vibration. Right? You can define it for either displacement or for input force. Right? If we're talking about transmissibility due to displacements, right, this is the ratio of the transmitted displacement or the output displacement to the input displacement. That sounds familiar, right? The ratio of the output to the input. Right, so what's the amplitude of my output versus the amplitude of my input? We do the same thing for force excitation as well. What's the ratio of the transmitted force, right, the output force, to the input force? And remember, looking at these equations, we're looking just at the amplitude of these two things, right? Just as the amplitude. We don't care what the vibrational frequency is, we just care about how much, right? So for vibration isolation, it's less about frequency, right? It's less about, well, this is oscillating at 100 hertz, right? Or 200 pi radians per second, and 615, okay? It's less about that. It's more about I have, 3 centimeters of displacement coming in, and I want to get that number as close. I want that amplitude to be as small as possible, right? Because if you have a low amount of amplitude, right, you have a low output amplitude, you've attenuated your vibration by quite a bit, right? This is all about magnitude. It's less about phase, right? What we're talking about. This is all about the magnitude of our Bode plots. So let's talk about this using a simple example, right? Our classic second order system here, right? So consider a simple mechanical system that has some base motion. And notice it has free ends now, right? It has free ends. So we can rewrite this equation as mx double dot plus bx dot plus kx is equal to bx dot b plus kxb. Right, we can write our transfer function. We get bs plus k over ms squared plus bs plus k, right? And then I can rewrite that in standard form, right, by dividing through by m. And I divide the bottom by m, and I divide the top by m. And that's where we're at. Notice that the denominator here is in the form s squared plus 2 zeta omega n s plus omega n squared, right? Okay. So all of them, why would we want that in standard form, right? Well, then we know what omega n is, right? And zeta. And if you know omega n and zeta, we know a lot about how this system is going to perform, not only in the time domain, but also in the frequency domain, right? We've shown that the frequency domain depends on omega n and zeta for the shape of our Bode plots, right? And what we can expect. So the transmitted displacement will depend on the magnitude of the transfer function. Since we want the ratio of the amplitudes, we need to get the sinusoidal transfer function. There it is. Right? We've done this before. Just plug in j omega for all of your s's, right? Substitute k over m for omega n and b over m for 2 zeta omega n. So we're just going to put this in terms of our standard form, in terms of zeta and omega n. And if we do some algebra, right, we'll get this on the bottom. G of j omega is equal to 1 plus j times 2 zeta omega over omega n divided by 1 minus omega squared divided by omega n squared plus j of 2 zeta omega over omega n. Right, so in this case, omega n is the natural frequency and omega is our operating frequency, right? Whatever our input is. And we can plot this, right? Well, before we plot this, let's simplify it a little bit, right? We're gonna take this omega over omega n business, and we're gonna call that beta. Okay, so beta is omega divided by omega n. It is the ratio of my frequencies, right? It's the input frequency divided by the natural frequency of the system. And so therefore, I can write my transmissibility equation for displacement as such, right? X over xb is equal to g, magnitude of g of j omega, which is the square root of 1 squared plus 2 zeta b squared, divided by the square root of 1 minus beta squared squared, plus 2 zeta beta squared. Right. So this is the equation for transmissibility. So if you know zeta, you know omega, and you know omega n, you're good, right? But we can also plot this. Right, but we can also plot this. We can see how this looks for changing frequency, but also for changing zeta. Okay. And that plot looks like this. So on the x-axis, I have beta, right, which is omega over omega n. Right? Obviously, omega n is going to be constant. So as we change omega, things happen. Zeta, each line represents a different zeta, right? And we kind of knew some of this already, right? Because transmissibility seems like it's just us reclassifying the magnitude of our transfer function, right? Which it kind of is. We're just repurposing that, and we're repackaging it to talk about damping ratio and frequency, right? And so first of all, the transmissibility depends on the damping ratio and the frequency ratio beta, right? Frequency ratio is just my operating frequency divided by my natural frequency. When zeta is equal to 0, right, when there's no damping, our transmissibility is infinite when beta is equal to 1. When beta is equal to 1, right, and zeta is equal to 0, remember we talked about resonance, right? When zeta is equal to 0, that means we have no damping. When we have no damping, our resonance is equal to our natural frequency, right, which means that at the resonant peak, we have infinity. This is a problem, right? This means that if you are operating with very low damping, right? If you're operating a system that has very low damping at a frequency near resonance, you are going to have an infinite spike in your amplitude, right? That's a problem. That's the Verrazano-Narrows bridge. Right? This is why, as mechanical engineers, you always hear people saying, or biomedical engineers for that matter as well, why you always hear people saying, we want to stay away from the natural frequency, right? We don't want to operate at the natural frequency. Why don't we want to? Because that is near our resonant frequency, and we don't want to be running at the resonant frequency in most cases. It's dangerous. Okay. That's what happens when zeta is equal to 0 and beta is equal to 1. Right? When beta is equal to √2, the transmissibility is equal to 1 for all damping ratios. right? So that's that. What's root 2? 0.7071, right? So when beta is equal to root 2, that's this point on this curve. Let me get the mouse right here. I'm not sorry, I didn't mean to say 0.70, it's 1.4. It's twice 0.7071. Right here. At this point, all transmissibility is equal to 1. What does the transmissibility of 1 mean? It means you get out what you put in, right? It means you are scaling by a factor of 1, which means you're getting out everything that you put in. The transmitted amplitude equals the base amplitude without any gain or loss. That's omega is equal to omega n times root 2. Sure. Right. So again, transmissibility tells us how much vibration we are going to let pass. A high amount of transmissibility means that you are amplifying the amount of vibration that we see, right? Certain systems, that's good, right? Like a PA system where you have to amplify the input signal, right? We want that. We want to be operating at a frequency that will amplify this for us nicely. However, most mechanical systems, we don't. We want to be operating with low, as close to 1 or less than 1 as possible, right? That's what we want. Now, certain systems will, certain design criteria will tell us how much transmissibility we can have, but we'll talk about that in a second. Right? All right, when beta is very small, right, this is equivalent to us having a very stiff spring, right? So beta is very small. That means that omega n is, well, that means omega is really small when compared, right? So we have a very low frequency, right? It means omega is much smaller than omega n. So you can see this here, right? For low beta, left-hand side of the plot, things are close to 1 as well, right? For all zetas. So they all start around 1, then they peak, and then they come back down, and they eventually do attenuate. Right? They eventually do attenuate. When the input frequency ratio, beta, is less than root 2, we have increasing zeta, and that decreases the transmissibility and improves vibration isolation. Right? So if we're operating below beta is equal to root 2, right? So if we're operating in this range here, right? We want a high damping ratio, right? Because that's going to lower this peak. Yeah? Right? Yes. Right, so again, this is the root 2 point. Anything less than this, you can see that as zeta increases, right, increasing would be moving down, right? This one's 0, this one's 0.2, 0.5, and 1. As these increase, zeta reduces, increasing decreases the amount of transmissibility. It's still over 1, but it's as low as it can be for zeta equals 1. When we have our input frequency that's greater than this 0.2 point, right, when we're moving to the right of this, increasing zeta increases transmissibility. So it flips, okay? So to the right of root 2 for beta, right, to the right of root 2, we actually want to decrease the zeta, right? So that root 2 point is where it flips, right? And you might hear about designs that have variable damping, right? And there's certainly things that we can do to control what our damping ratio is. based on what our operating frequencies are, right? But I think the general rule of thumb here, right, for us to think about is a high transmissibility means that you are transmitting a large amount of vibration, and a low transmissibility means that you are not, right? So depending on your application, most of the time for mechanical biomedical engineers, right, we want to minimize TR, right? Most of the time. TR less than 1 occurs only after that root 2 point, right, for beta. We never get a transmissibility less than 1 to the left of this point where my mouse is. For the minimum transmitted force or motion, we want to choose vibration isolation mounts with undamped natural frequencies that are much lower than the expected input vibration frequency, right? So we want beta to be high. We want beta to be as large as possible, right? So we want to look at our system, we want to understand what omega n is, and we want to try to operate in a range that is larger than, that is significantly larger than omega n, so that beta can be as large as possible, right? What affects omega n? Well, remember, omega n is k divided by m. So that's controlled by the parameters of the system. So if we're designing a system to have low transmissibility, we can figure out what type of springs change our omega n, right, for the expected operating frequency. If possible, we want to select mounts with light damping for minimum transmissibility, only for beta greater than root 2, right? So if we know, if we've designed and we've made beta larger than root 2, then we can say, well, how do I affect zeta, right? Well, zeta is what? 2 zeta omega n is just b over m, right? And we had that equation on the master sheet that tells us what zeta is in terms of bm and k, right? So if we know what m and k are to get that omega n that we need, then we can fool around with the other parameters with b to get a zeta, right? And when we're to the right of the root 2 point, we want zeta to be as low as possible. And when we're to the left of it, we want it to be as high as possible. It is possible, and in certain cases, it's pretty common, that you're not trying to hit a single range, a single frequency, but you want to operate over a range of frequencies, right? Not all asphalt, or to go back to the car example, not all asphalt is poured equally. It's not all a uniform, I know for sure this is going to be 1,000 radian per second signal, right? It's not. It varies, right? So we want to be able to work over a range of frequencies. So many times the disturbing input frequency may not be constant, but might be in a known range. And the isolator design must consider a range of betas, right? So you have to look at what beta looks like over your range of input frequencies. And so the trade-off, right? The designer may need to balance your transmissibility requirements with other design constraints, like response times, settling times, amplitudes of, right? So you might have to balance time domain criteria with your frequency domain parameters, right? And so that's kind of the game, right? Is over this range of frequencies that are known ranges of frequencies that I know this is going to operate over, how do I minimize the transmissibility, right? Okay. We'll watch this one.
Right, this short session is on vibration, but it's specifically to do with transmissibility. One of the formulas that we're going to come across in terms of vibration control is one to do with transmissibility. And it's one linked to something called vibration isolation. So T in this case represents the amount of transmission of vibration from source to reception. And it's basically a function of the driving frequency of the vibration and of the resonant frequency of the mass spring system. So in this particular case, there are two expressions that we can use. The first one that I'm writing down basically has this formula where the F of F0 squared is taken away from the 1. This is for situations where the F is greater than F0. So in this particular formula here, the F0 is the resonant frequency or natural frequency of the system, and F is the driving frequency. The other formula that you can have, okay, is when F is less than F0, and the only real difference with this is that the transmissibility this time is 1 minus F over F0 squared. Okay? To know why there's a difference, you need to have a look at the notes and look at the lecture notes that I cover to explain that in a bit more detail. In this particular tutorial, I'm going to take this first formula, and what we're going to do is look at rearranging that formula for F0. Again, I'm doing this because this is a very, very popular exam question in both the general acoustics paper and the noise control paper. So it's a particular important maths to do. So we're going to use this formula here, okay, and we're going to rearrange that formula for F0, which is the natural frequency of the source. So first thing to do is I'm going to take this term here and put it to the top and take the T and put that at the bottom. So the first stage is to end up with F of F0 squared minus 1 equals 1 divided by T. So all I've done is switch these two terms, okay? That's all we've done there. So we've got the F0, it's tied in here. There's a minus 1 there. Well, let's just basically take that minus 1 across, and it becomes plus 1 on this side. Okay? So we end up with that. We might as well now square this out. So this becomes F squared over F0 squared equals all that. Okay, so we've just squared that out. The F0 squared is tied up in the division sum here. So what we can do now, I'll put a bracket round that because I'm going to switch these two terms around. So the F squared stays where it is. The F0 squared goes to the top. And this term here, the 1 over T plus 1, goes to the bottom. Now when you get to that stage, you've probably already keyed in some numbers into the formula. So this particular denominator here won't look as clumsy as what it is here. Okay, so you've probably given the T value, and that will be a single figure. To make this into simply F0, we just take the square root of this term. Okay, so basically all we do is square root both sides and we end up with that. So as I said, this is a very common manipulation that you need to do, particularly in an exam situation. The other thing that you often have to do is to rearrange it for F as well. Okay, so again, it's a similar process, but obviously we go our separate ways when we get to this stage here. Okay, so that concludes that brief tutorial.
Fantastic. All right. So we're gonna watch one more video, the other Bode transform one. But before we get to that, I want to take a look at this plot again. Okay. Understanding how transmissibility is affected by zeta and omega and is important, right? It doesn't matter. So essentially, right, remember, transmissibility is the magnitude of our system, right? So if you're given a Bode diagram, you can tell the transmissibility of it at a specific frequency, right? Because this is just the magnitude, right? This is just the magnitude here, okay? So keep that in mind. Right? If you're looking at Bode plots for magnitude, you are looking essentially at the transmissibility for a system in a specific configuration, right? Keep that in mind. Let's get back to that other video. There we go. Sketching.
Welcome back to Control System Lectures. Just to let you know, I've just dropped the prefix on the video titles because they were taking up too much real estate. But these videos are in the same series of lectures, so if you're subscribed to Control Lectures, you'll still receive these updates. This video is a continuation of the Introduction to Bode plots that I posted last week, and here I'll discuss how to sketch a Bode plot by hand directly from the transfer function. And this first video will only cover when the transfer function is a constant gain. Now you might be asking yourself, why do we need to learn how to sketch Bode plots by hand when we have computer programs such as MATLAB that can generate a Bode plot with the touch of a button? I've been a controls engineer for over 10 years now, and to be honest, I very rarely ever had to sketch a Bode plot by hand. But while you might never actually need to do this, there are still at least two compelling reasons to learn this skill. The first is that by practicing this, it gives you an intuitive understanding of how poles and zeros affect the frequency response of a system without having to actually ever plot the response. And the second is that it gives you the ability to estimate the transfer function just by looking at the frequency response of a system. And this is particularly handy when you're trying to estimate a transfer function, say from the output of a frequency sweep on a new structure that you're building. So recall now from the introduction to the Bode plot video that when you have a transfer function h of s, you can calculate the steady state frequency response by setting s to j omega. Then you can solve for the real component and the imaginary component and rewrite h of j omega as just the real component plus the imaginary component times j. If we were to plot this on a real and imaginary axis, where the real component is just drawn on the horizontal line and the imaginary component is drawn on the vertical line, the gain of the transfer function for that particular frequency is just the length of the line from the origin to that point on the real imaginary axis. That can be written as the square root of the real part squared plus the imaginary part squared, or in shorthand notation you can just put these two vertical lines around it, which means the magnitude of h of j omega. And the phase is just the angle of the vector off the positive real line. And we can write this as the arctangent 2 of the imaginary part and the real part. And in shorthand notation, you can just write this as the argument of h of j omega. We can establish the sign of the phase by which side of the real line it appears on. In this case, it might be about 45 degrees. If we continue it a little bit further, it might be 120 degrees. But if we go down below the real line, then it becomes negative, so negative 60 degrees in that case. So let's review the simplest transfer function there is, which is a constant, and see how that is represented on a Bode plot. In this case, the transfer function h of s is just equal to k, which can be any real number, either positive or negative. And we can represent this in block diagram form by showing that the input gets multiplied by k and becomes the output, or u of s is the input and y of s is the output. Now we can apply the gain equation from above, which is the magnitude of h of j omega, to this constant k, which is just the magnitude of k, which is a positive k. And the phase, which is the argument of h of j omega, is equal to the arctangent 2 of the imaginary part, which in our case is 0, and the real part, which is k. And again, k can be either positive or negative. And that's why we're using arctangent 2 to keep track of the sign. Let me explain it this way. If we were to plot this on the real and imaginary axis, then all of the values would lie on the real line since there is no imaginary component. If k is a positive number, then it'll appear on the right side, and if it's a negative number, it'll appear on the left side. But one thing to note about both of these positions is that whether k is positive or negative, the point still exists exactly a k distance from the origin. And since gain is the distance from the origin, the gain is always k for constants, whether they're positive or negative. Phase, on the other hand, is different. For the first value, a positive k, phase is 0 degrees. But for a negative k, it's 180 degrees off the positive real line. Traditionally, we would just say minus 180 degrees, but they're equivalent. So if the constant is positive, then the phase is 0 degrees, and if the constant is negative, then it's minus 180 degrees. And that's why I like to use arctangent 2, because it keeps track of the sign of k for you, so you don't have to think about that. If you just use arctangent, you'd have to remember to subtract 180 in certain cases and not in others, but I'd prefer not to remember that and just use arctangent 2. So now that we have our gain and phase, how can we represent this on a Bode plot? Well, the gain is easy. Like we said before, it's just k for all frequencies. But to plot it on a Bode plot, we have to convert it into decibels, which is just 20 times the log base 10 of the magnitude of k. And again, it's constant for all frequencies, so it's just a horizontal straight line. And luckily for this example, phase isn't much more difficult. Phase is 0 degrees when k is positive, and it's minus 180 degrees when k is negative. But again, the phase stays constant either at 0 degrees or at minus 180 degrees. It stays constant across all frequencies. So if it's not too intuitive looking at this at a Bode plot or on a real and imaginary axis, another way to think about this is just to input a sine wave through the block diagram. A sine wave input produces a sine wave output whose amplitude has been adjusted by a factor of k. Also, if the input was a positive sine wave and the k was a negative 1, the output would just be flipped along the vertical axis like this. Of course, as you can see, this is just a phase shift of negative 180 degrees. So let's do one last example, and this is with a very simple electrical circuit. Let's say you had a voltage generator whose output was a sine wave. And the positive voltage was then applied to a resistor, and both of them were tied to ground. The resistor has resistance R. A current would be induced, I, and using Ohm's law, we know that V equals IR. But if we wrote this as voltage changed over time, it would be V of time equals I of time times R, since resistance wouldn't be changing. We could take the Laplace transform of this equation and then solve for the output I over the input V and get 1 over R, which is the transfer function for this simple circuit. And since the resistance isn't changing with time, 1 over R is just a constant, and we could represent this on a Bode plot as a constant gain at 1 over R with a phase shift of 0 degrees. I know it's 0 degrees because R is going to always be positive. So this is what the Bode plot would look like for a very simple constant transfer function. Of course, most transfer functions aren't this simple. They can be made up of any number of complex or real poles and zeros. But the step-by-step example here of how we go about generating a Bode plot still holds up for those other parts. And so what I'll do in the next couple of videos is expand on all of those different types of transfer functions and then show you how to approximate them very easily using just a few simple concepts. And since the next few videos all tie together nicely, I'm not going to wait a week to put them out. I'll try to get most of them out over the next couple days. So if you don't want to miss anything on how to sketch Bode plots, don't forget to subscribe. Thanks for watching.
Dr. D, I think you're still muted. I don't know if you're talking to us, but
No, Cat, you're muted. Okay. Jeez. But anyway, like I was saying, that's all I've got for today. Next class, we will go over rotating unbalance, which is like the last piece of the puzzle. Do a bunch of problems, and then probably next week on Tuesday, we will do a case study all the way through from tip to tail, how we use everything that we've been talking about. Okay. Hopefully tie it all up together. Bring questions, right? Bring all that, right? And that's it. Have a great rest of your day. I'll see you guys on Thursday.
Thank you. Have a great one.
Thank you.
bye. Have a nice day.